Hello and welcome. Today we're going to talk about a new proof that I've found about how we can find an expression for the summation of our derivatives. Now, in this proof, we're going to use the summation of derivatives and the Fourier transform and the geometric series. And this will provide a deeper insight into what we already have discovered, and we'll find new properties which will help us understand what we're actually doing. I personally find this proof to be more elegant, but of course, beauty is to the eye of the beholder. Back to the basics. First problem at hand. The problem is there a compact way to find an expression for the sum of derivatives from the zeroth derivative, which is the function itself, to the nth derivative? I also want to point out the property of the geometric series, namely that if you have the summation from 0 to n of x to the power k, then this will be equal to 1 minus x to the power n plus 1 over 1 minus x. Lastly, we're going to look at the property of the Fourier transform. Namely, if you differentiate your function in the real world with respect to the variable of that function, then in the Fourier world, you will multiply by I times omega. Of course, you have different versions of the Fourier transform, but I will be using this one as this is the simplest to use for my proof. Okay, so let's look at what we have. We want to find the summation of our derivatives. And if we take this to the Fourier space, we will see that we have our Fourier transformed function times I omega to the power k. But if we sum it from 0 to n, we can also sum it from 0 to n in the Fourier space. This means that we now have a geometric series, and we can express this geometric series as you see in the middle of your screen, namely as 1 minus I omega to the power n plus 1 divided by 1 minus I omega. Now we're going to separate that in two parts, so we have two distinct functions, namely I omega to the power n plus 1 times the Fourier transform divided by minus 1 plus I omega minus the Fourier transform of a function divided by minus 1 plus I omega. Now, why do we do this? Well, that is because now we can see it as a convolution. Because actually, if you divide by minus 1 plus I omega, you multiply by 1 over minus 1 plus I omega. And that is a famous Fourier transform of the unit step function times e to the power x. So now we can convert our Fourier space function into the real world again, and we find that we have a convolution between the nth plus 1 derivative of a function minus our original function and the unit step function times e to the power x. Now we can write out this convolution integral. As you can see, as we take e to the power x minus tau, we see that e to the power x is independent as you multiply it, and thus we can take it out of our integral. This means that we've already found an expression for our summation. But if we divide by both sides with e to the power x, we find our original integral again. But this time we have the lower bound at minus infinity, and we'll get back to that. But just think how utterly fucking amazing this is. We just came up with the idea to transform it in the Fourier space, see what we get, and we actually find the solution to a problem in a rather easy manner. Of course, it is still a bit convoluted, one might say. It is, in a way, quite straightforward. And it also gives a bit more insight in what's actually happening. But since we do not know what happens at minus infinity, for now it's best to just define it in a bounded manner. And that's what we're going to do. We simply take the function twice first bounded by y, and then subtract the integral when it's bounded by x. So we have our two variables. And since you subtract them from one another, you get an integral which is bounded on both sides, and we can express that in our summation. Now we're going to look at integration, because of course we can also use the same principles we've used for differentiation to integrate it. You don't always have to start at 0, but you can just start at m and end at n. Now you can just read this through, but it doesn't really change a lot. It just makes it more general, which is quite useful later on. But now we can go further. Let's say that we have a function f(x) for which holds that when we take the Fourier transform and the modulus of omega is bigger or equal to 1, then the Fourier transform will always be 0 at that particular omega. We can actually do something very pretty. Namely, if we look at the summation in the Fourier space, we can take n to infinity, because as we take n to infinity, it converges always to 0 because our modulus is always smaller than 1 when a Fourier transform function has any value which is not 0. This is an amazing property which you can now work out. And look what happens. Well, as you work through it like we did last time, then you'll see that we actually miss one part of our function. So this is actually the property to which the function must hold for the summation to be able to converge after taking the derivative of the function infinite amount of time. And that is actually very enlightening. Now we of course write the general form. Now we can also integrate to infinity. And here we have the same story, but actually the one that disappears is m as we take n to minus infinity. But since now we have 1 over I omega, we want the modulus of omega to be bigger than 1. Thus, we want that our Fourier transform function is 0 for all omega which has a modulus which is smaller or equal to 1. Now we can work this out just like we did last time and see that we only have the other part of our integral. And this is a property to which infinite integration must hold to be convergent. So now we can say whether a function will converge if you integrate it an infinite amount of times, and whether it will converge if you differentiate it an infinite amount of times. Now, I can already hear some of you thinking, well, don't you have to add a constant when you're actually integrating? You know, the old famous integration constant. Well, this is not the case. Why is this not the case? We're going to look at an example, which is essential in understanding that, but let me just give you the gist of it. If you have a constant and you take the Fourier transform, then the only value it will have is at omega is 0, and elsewhere it will be 0. And since we have defined our integrating limitation for our function f(x) to be only non-zero if the modulus of omega is larger than 1, we can comfortably state that we do not get an integration constant each time, as the omega of 0 must always be 0. So this is some sort of limitation which also prevents us from actually having this problem. But now we're going to talk about taking the primitive of a constant endless many times. Well, if you think about how integration works, or rather find the primitive, you'll see quickly enough that if you do that and you sum from 0 to infinity, you actually get e to the power x. But how can it be? Well, the basic answer is that which just happens at omega is equal to 0. But you can imagine that if you integrate, you divide by 1 over I omega. But if you take it to 0, 1 over I omega goes to infinity. And this is really quite problematic. But we just have to refine our statement because there is not a lot of freedom at omega is equal to 0. The only thing that you can plug in are constants. And since you already know that if you integrate this infinite amount of times, you get e to the power x, and if you were to differentiate, you would get 0. We do not have a problem because we already have all the information that we need to set up our rules. Now, we actually have information about to which properties a function must hold to have certain other properties. If f of omega is 0 for the modulus of omega being bigger than 1, then differentiating converges. If we have that the Fourier transform of a function is 0 for the modulus of omega between 0 and 1, then integrating converges. And if it's only non-zero at exactly 1, then it fluctuates. An example of this is the sine. If you differentiate it or integrate it infinite amount of times, it will just look back on itself. So these are stable in a way. So here we have a summary of what we've actually discovered. And perhaps the most interesting thing is that due to our limitations in whether a function will converge or diverge if we take every sum of the derivative or primitive, we actually find that there's only one function for which you can integrate it and differentiate it in an infinite amount of times, namely the constant, because for the constant it is convergent for differentiating as well as for integrating. And this actually gives us a constant times e to the power x. And I think that is just pure mathematical beauty. Don't you think so? So, uses. I have literally no idea. I don't know what you can use it for. I hope maybe someone can use it for certain proofs or in engineering, but I've no idea. Anyway, it's really pretty, and I hope you find this interesting. If you have questions, please do ask. I will be glad to answer them. And with that being said, I would like to thank you for watching this, and I hope you enjoyed this video.